In this video, we're going to look at properties of hydrocarbons and also reactions of hydrocarbons. So let's start with hydrocarbon physical properties. The polarity of hydrocarbons is nonpolar. It's only made up of carbon and hydrogen. Intermolecular bonds are London dispersion forces only. And the solubility is soluble in non-polar solvents. Boiling point and melting point are fairly low, but depending on size / number of carbons, right? So what I mean by that is that the more carbons a hydrocarbon will have, the higher the melting point and boiling point. So we can see this right here. State at room temperature. If it's only 1 to 4 carbons, then the state is going to be a gas. But if the if the number of carbons in the molecules goes between 5 and 20, then it's going to be a liquid. And beyond 20, you end up with a solid. So a lot of hydrocarbons come from oil refinement, so we'll quickly go through this. Crude oil is a complex mixture of hydrocarbons. Part of the refining process involves separating the oil into various fractions according to the boiling point in a process called fractional distillation. Larger hydrocarbons have higher boiling points and are more viscous and dense. Since smaller hydrocarbons are generally more useful, crude oil is exposed to heat and a catalyst in order to break them up into smaller units in a process called catalytic cracking. Okay, let's look at hydrocarbon reactions. So the first hydrocarbon reaction we're going to look at is combustion. All hydrocarbons undergo this reaction with oxygen to produce carbon dioxide and water. So 2,3-dimethylbutene undergoes complete combustion. Let's draw that out. 2,3-dimethylbutane, so we're going to start with butane, so 4 carbons bonded together. And then 2,3-dimethyl means I've got a methyl group on the second and a methyl group on the third. And then the rest of this now I can simply put in the rest of the hydrogens. And then plus oxygen goes to form CO2 and H2O. I'm going to start with my carbons. 1, 2, 3, 4, 5, 6. I've got 6 carbons. I'll put a 6 right there. And then I look at my hydrogens, and I have 14 hydrogens, so I put a 7 there. But this right here yields 19 oxygens, and the subscript on oxygen here is an even number, so I'll say 19/2, just to make this easier on myself. If you want to eliminate this this rational coefficient, multiply everything by 2, and then you would have 2, 19, 12, and 14. Because of double and triple carbon bonds, alkenes and alkynes are more chemically reactive than alkanes. And this is due to the electrons in the pi bonds protruding more outward. These bonds are more prone to quote-unquote attack. So that's the location of overlap, or the correct orientation when we talk about chemical reactions. It happens at the double or triple bond. So let's bear that in mind when we look at alkenes and alkynes. The double and the triple bonds will be the site of chemical reactivity. So what are we going to do with alkanes? Alkanes are things that have single bonds only. And so it says, due to the strength of the carbon single bonded carbon bond, they are unlikely to break and cause a reaction. So as a result, alkanes undergo substitution reactions. So substitution reactions are where something is taken out and something is put in its place. So the general formula for halogenation by substitution, whereby a halogen substitutes a hydrogen atom in an alkane, is we have R CH2 R prime, okay, plus X2 goes to form. And this is where having like maybe some, like a red, a blue, and a black pen comes in handy. We're going to continue to draw this in blue. Okay, but what we will draw instead now is we will show where the substitution happened. So one of the H's came off, one of the X's went on, the H that came off joined the X right here. And so what I would put in black underneath is just the names. This is an alkane, this is a halogen, this is an organic halide, and this is a hydrogen halide. So let's do a specific example of ethane and bromine. So ethane is an alkane, eth being the prefix for two carbons. So I write here H3C-CH3. I'm going to react that with bromine. Note what it says right here. Fluorine substitution happens vigorously, but the other halogens will require UV or heat to react with the alkanes. These single bonds are fairly unreactive. So over the arrow, I'm going to write UV or heat to facilitate this reaction. Then I'm going to write H3C, CH2, and I'll put a Br over here. But what you will see is that this has lost a hydrogen because one of the Brs has now been added to the alkane, and the hydrogen that was here got substituted off. And then underneath we write ethane, bromine. This right here, we call this bromo for the bromine, bromoethane, because the parent chain is ethane, but it has a bromine on it. And this is simply hydrogen bromide. We can then take bromoethane and substitute it again by this process. So this one I'm not going to color code, I'm just going to show you. It's got the bromine, so I'm literally taking this molecule right here. I add more bromine to it under the presence of UV or heat, and I can get another bromine added on. I'll just show you that the other bromine will be added on right there, and the hydrogen comes off. I'm not going to bother with the names underneath. You know what? Maybe I will. Bromoethane, bromine. This right here, because there's two bromines, this is going to be dibromo, and it's on the first and second carbon. So 1, 2, dibromoethane, and again, hydrogen bromide. Okay, moving right along. Aromatics, remember aromatics means that we're dealing with benzene, and benzene is that very stable carbon ring with alternating double bonds, or we can show it like this to show that there is a pathway of delocalized electrons within the molecule. So due to its unique bonding structure, benzene has a stability and reactivity similar to alkanes. As a result, benzene also undergoes substitution reactions. So benzene is going to substitute, it's not going to be an addition reaction. Okay, so because it is so unreactive. So the general formula, we're going to use these symbols right here, and we're going to call it, we're going to start with halogenation by substitution. The catalyst that we're using here is FeBr3, not Fe, so let's make that correction right there. So a halogen substitutes a hydrogen atom in benzene in the presence of a catalyst. So my general formula is, I'm going to have benzene, okay, that's my formula for, that's my symbol for benzene, plus some sort of halogen. Remember, halogens are diatomic, and then we have over here FeBr3, okay, and then we will have onto the benzene we are going to add one of the halogens, one of the hydrogens on the benzene comes off and joins the halogen. Let's be more specific. Let's actually do one right here. Write the reaction between benzene and chlorine. So I'll draw my benzene ring right here. I'll do this one with alternating double bonds. Okay, and then I have my chlorine in the presence of iron 3 bromide. Then one of the chlorines, and then, you know what, I'll stay consistent. Sorry, guys. One of the chlorines will come on. Remember, each of these carbons has a hydrogen on it, and so the hydrogen comes off. And you know what, I'll do this one right here. Making a bit of a mess here, guys. Sorry. Trying to get through this quickly so you don't have too much to watch. Okay, yeah, sorry for the mistake there. So yeah, okay, so the Cl goes there and the HCl is left there. So let's write these names. This is benzene. This is chlorine. And there's just one chlorine on the benzene, so this is chlorobenzene. And this right here is hydrogen chloride. Okay, let's look at nitration by substitution. So it's the substitution using nitric acid in the presence of sulfuric acid. So I have my benzene, I'm going to add nitric acid. Okay, I'm going to put H2SO4 as my catalyst, and then I'll end up with a nitro group on the benzene and water. Let's show this using actual structures. So benzene is right here. And in this case, I'm just going to do the actual benzene ring right there with the circle inside. HNO3, H2SO4, with NO2 and HOH. You can also write that as H2O. Okay, and maybe I will color code this right here. I'll put this as my NO2 gets placed there, right? And so as you can see, NO2 is added, which means I have an extra oxygen. So I had hydrogen to oxygen left over in this molecule, plus the other hydrogen came off. Again, I'll color code that. You don't have to if you don't want to. It's not the biggest deal if you don't. Okay, and I'll write benzene. This is nitric acid. This right here is nitrobenzene. And this is water. Okay, alkylation by substitution. So that's substitution using an alkyl halide in the presence of a catalyst, AlX3. So my general formula right here is going to be my benzene plus my alkyl halide. Okay, in the presence of a catalyst, AlX3. Okay, and then I'll have the R group stick onto the benzene ring, and then I have HX. So we'll do write the reaction between benzene and 1-chloropropane. So I'll put my benzene right here. 1-chloropropane, that just means that I've got a chlorine on a propane structure. All right. So as we can see here, this is my, that's my R group, right? And that's my halogen. So what's going to happen here is the benzene ring is going to have the R group attached to it. And then the chloride is going to bond with the hydrogen that comes off the benzene. And we'll write the names. Benzene, and this is chloropropane. Let's say 1-chloropropane. This right here is called propylbenzene. And this is hydrogen chloride. Okay, so these were all my substitution reactions, and these are substitution reactions because the organic substance that we're reacting with is very stable. So substitution reactions happen when you have a very stable organic compound and we just add something on but have to take something off. This is in contrast with what we're going to learn right now. These are reactions of alkenes and alkynes. These are called addition reactions where we just add something onto the molecule. We don't have to take anything off. And that's because the double and triple bonds are so reactive that that's the site of reactivity. So let's not delay. Let's get started right away with these ones. The first type is halogenation by addition. So we're going to add to a molecule using a halogen. And I'm going to jump right into using molecules. So we're going to start with ethene. Okay, so 2 carbons, so eth, and then double bond, so ethene. And I'm going to add bromine right here. Okay, and so now what's going to happen is I am simply adding to the molecule, and I'm always adding where there's the double bond, because that's the site of chemical reactivity. So I go H2C, and that becomes a single bond now, and that's because each of the bromines has been added across the double bond. So this right here is ethene, this is bromine, and this over here is 1,2-dibromoethane. So it became an alkane in the end because we added bromine to it, causing that double bond to become a single bond. Hydrogenation is the addition using hydrogen. Okay, and in this case right here, I'm going to use propene. So H2C double bond CH, CH3 plus H2. And again, it always happens at the site of the double bond. So I'm going to have H2C single bond CH, CH3. And each of the hydrogens adds on to this location here. But you can see here, this is just a regular hydrocarbon that is all single bonded. And this literally just becomes propane. So I went from propene to propane by adding hydrogen. Hydrohalogenation is the addition using a hydrogen halide. Okay, and so I have propene here. And I have, we'll say HCl, hydrochloric acid. Okay. This one's a little trickier. In this case right here, the hydrogen will always be added to the carbon with more hydrogens, whereas the second half of the molecule goes to the carbon with fewer hydrogens. So what we end up with is H2C-CH-CH3. And in this case right here, my H is attaching to the carbon with already more H's, and this is the chloride is attaching to the other carbon. Okay, let's name these. This is propene. This is hydrogen chloride. And this right here is going to be 2-chloropropane. All right, hydration. That's the addition using water. So I'll draw out my propene again. H2C double bond CH, CH3. And in this case right here, I'm going to write HOH. And the reason I'm doing that is because, again, the H always goes to the carbon with more H's, and the OH goes to the carbon with fewer H's. And so this becomes H2CCH3, and the H is down here, and the OH is over here. So propene, water, and this right here is actually an alcohol because of the OH, and so we call this 2-propanol. And you'll learn how to name alcohols later. Okay, so how do you know where to put the hydrogen when faced with, this is actually hydration. in hydrohalogenation? Well, that's Markovnikov's rule. And Markovnikov's rule is simplified by saying the rich get richer. And what we say there is that hydrogen is added to the carbon with the most hydrogens. Okay, so in an addition reaction, you just basically put the hydrogen where there already is more hydrogen. Okay, and we saw that over here. So note on alkynes. Alkynes are triple bonds, and alkynes may add 1 mole of reactant in what's called a controlled addition. And if we do that, then it forms an alkene. So it goes from a triple bond down to a double bond. But if you add 2 moles of reactant in the presence of excess reagent, then you form an alkane. So 2 reactions here, the controlled addition of bromine with propyne. So propyne would be just as follows: HC triple bond C bonded to CH3. Okay, that's propyne, and then we add bromine, and we're just adding quote unquote 1 mole in a controlled reaction. And that would take us from this triple bond down to a double bond. So I have HC double bond C CH3, a bromine here and a bromine here. So this is propyne, this is bromine, and this is going to be 1,2-dibromopropene. Okay, addition of excess bromine with propyne. So I take my propyne again. And if I have excess bromine, then I'll say 2 Br2. And now I'm going to go down to an alkane. Okay, and so I'm going to have bromines here and here, but I'll also have bromines here and here. So this is your propyne. This is your bromine. And this would be 1,1,2,2 tetrabromo propane. Okay, and there we have it. Those are the reactions of hydrocarbons. Quite a few of them, but once you see the patterns, it becomes a bit more straightforward. Thanks for watching.